Hello class, I am making this video as a quick review of the major concepts from chapter 5 that we discussed prior to break. Just as a refresher, because a lot of these formulas we're going to be using um, a lot in 5.4, 5.5, and 5.6, which are notoriously complicated subjects. Well, there's just a lot of math, a lot of numbers, a lot of formulas. So I wanted to review the key ideas from beginning of chapter 5, i.e. compound interest. So in chapter 4, we talked about simple and compound interest already. So just to recap, this is 5.1 of our book. This is 5.3. If you want to read more into it, that's where I would start for understanding those formulas, which again, they look a little bit different in the book based on the change in variables. But we did these examples a while back and discussed kind of how simple interest is linear, whereas compound is exponential. And it grows based on the repeated multiplication of compounding, i.e., every uh, every so often, based on the number of times it's compounded, our principal is growing via multiplication, because if it grows by 5%, that's multiplied by 0.05 and then added. So, and if the balance continues to grow based on not just the principal, but based on its current balance, the current balance will also have another percentage. Basically, it's a percentage multiplied by percentage multiplied by percentage, which is what compounding means, which is why it ends up being exponential, because our percentage of growth is repeatedly multiplied month by month by month by month, which gives us that type of compounding. Um, and then compounded continuously 5.3 is that sort of magic formula where the confusing, or not confusing, but more complex compound interest formula, uh, if we take the limit as n approaches infinity, becomes simpler, in e as the base of the exponential function. Anyways, in the chapter 5 packet, where if you did have to miss class before break, you might not have gotten a hold of one of these, but you can print it out from Canvas if you need to, which I would strongly recommend, because math is really important to do by hand. And if you just follow along the videos, everything may make sense and it might be great. But if you're not really doing math and practicing by hand, uh, it's not going to stick as well. So what I recommend is try out the examples, and even as I'm going through the examples on YouTube, you can pause me um, and work on the example and see if you can figure it out before I do it. And then you can check with what I do to see, did I get it right, assuming I didn't mess it up, of course. So anyways, but the last thing, let me try to wrap up the review video, but um, in the chapter 5 packet, I just mentioned that I changed my approach a little bit to try to match the book in the formulas and the structures in how it presents. So basically, when we're looking at the compound interest formula, I made the substitution where, let me go to the whiteboard here for a second, where I called let me get a highlighter here, the r divided by n, which is called the periodic interest rate. That's not something I invented. It's a common way of describing it. Basically, because the yearly interest rate, or the APR, is r as it was described in the formula. Say, for example, 4% or 6% is easier. Um, if it's compounded monthly, it's not going to grow by 6% per month. So when I'm adjusting my formula to multiply on a month by month basis, I need to normalize the interest rate to the time frame. So if it's done 12 times per year, we'd take that interest rate, say 6%, and divide by 12, which would leave with 0.5%. But anyways, it's going to make sure that it's growing based on the periodic interest rate. So what I'm going to do is call that little p. And now this is not ideal because capital P is already in this formula. So this is another thing I mentioned in class, is that I'm going to draw my lowercase p's a little bit curlier, more like the Greek letter rho, just to distinguish them from capital P. But when it's typed out in the packet, you can tell, because little p and capital P look a little bit different. And also, I'm going to call the variable in the exponent n times t as just capital N. And all compound interest formulas will I'll be presenting them like this here on out. But it's always given the same assumption that P is equal to R over N. And this is all in the packet as well. So little p is equal to R over N. And then capital N is equal to lowercase n times t. And that's the basis for our compound interest formula. It just makes it look a little simpler and cleaner. And the value to this is that when we're dealing with present value and annuities and amortization, these formulas are used over and over and over again, and the simplification is worth it, I promise. So that being said, let's get back to, and also stuff like APY and effective interest rate and solving those other problems we did as well. So I would review that if you missed that, because it's some tricky ideas in there, as well as the slides. But I'm trying to get into the new stuff for lecture for this week while reviewing the more critical ideas for going forward. But present value is the last thing that's important to review because it's also it's used quite a bit with amortization. So anyways, I wanted to remind you that the difference between, well, really there is no difference between present value and future value. It's the same idea. Present value is more about trying to figure out, if I want to have this much money in the future, how much will it be worth today? Like if I'm trying to go, like the formulas that we worked on in class are more about, well, if I have this starting amount, what's the future value given present, like the current amount, present value, future value. But let's say I wanted to, my goal was to have, say, $1,000 at the end of 5 years, and I want to know how much do I need to invest in that account to get there. That's exactly the idea of present value. It's like, well, what's the present value of that future goal? And to solve for present value, we did this on Thursday before break as well, but it's been a long time. So is basically just to solve for p. So if I want to solve for p there, I could divide both sides by, because what I have is p multiplied by 1 plus p to the little p to the n. I could divide by 1 plus p to the n on both sides of the equation. And that will, of course, cancel out the 1 plus p to the n on the right-hand side and solve for the principal, or as we call present value. But really, P just stands for present value. It's like I want to know, well, what is the principal given a particular future value? And it's often written as you see it in the packet like this. Present value is equal to the future value times 1 plus p to the minus n. And remember, that's the same thing as what I wrote over there, because negative exponents are the same as division. As we talked about a lot, like probably way too much in chapter 4, but f times f1 plus p to the minus n means the same thing by reciprocal, because I could change this expression to a positive exponent by dropping it to the bottom by rule. So anyways, this is what we call our present value formula. And when we're calculating present values of things, this is where you can begin. But my key point here is that it's not really a different formula. It's the same formula as the compound interest formula. So if you really remember the compound interest formula, and in this form it's a lot simpler, you can just remember the present value by switching f and p and making the exponent negative. So present value is equal to future value times 1 plus p to the minus n. And this is our present value formula. So typically when you see in the book or whatever, find the present value, this is just where we begin. And really what we're doing is we're kind of going backwards in time. So let's look at we did some examples last week, and also a reminder that if you're doing continuous interest, you want to use the continuous, the present value of continuous interest, which is just the same PE to the RT, but we're switching F and P and making it negative for the exact same reason. But let's, I'm gonna wrap this video up, and in the next one we'll do an example of what we call net present value, and we'll get into that, which your first lecture quiz will be on exactly this. Anyway, see you in the next video.